Brian Washburn. What I'd like to do now is solve the equations of motion for quadratic air resistance. So last time we derived two coupled first order differential equations. So again, let's kind of review. What I have here is this, we derived these equations before. So if I can write F equals ma in a vector equation, so I say mass times acceleration, v dot, is equal to the net force acting on the projectile. We have gravity plus the quadratic air resistance term that acts in the minus v hat direction. Okay, where v hat is the unit vector along the direction of the velocity. So it's the velocity divided by its magnitude. Okay, so what we want to do is we want to look at the solution, and let's first consider a generic or a general condition where I have a projectile of mass m located at the origin initially, and it has some initial velocity shown here. And so I want to solve these equations in a Cartesian coordinate system. So writing v hat in a Cartesian coordinate system, it's just, again, two dimensions. Vx via x hat plus vy y hat divided by the amplitude of the speed. Okay. So now what I do is if I take this equation here and stick it into this, I want to break this up into x and y components. We did this before. Note that you notice that if you look at this particular term here, I have v squared times v hat. Let's write that here. So here I'm going to get v squared. Well, v squared is going to be vx squared, sort of then vy squared times v hat, and v hat is going to be vx x hat plus vy y hat divided by the magnitude or the speed. Now if I look at that product, I have this thing here is this is the square of this thing here. So then what I can say is I have here v. Let me erase that, sorry. So I have, this is the square of the denominator. And so what I can do is I can just divide the two. I'm going to get vx squared plus vy squared square root times vx x hat plus vy y hat. Okay. So now let's break up this equation here all in terms of x and y components. Okay. So in the x direction, I'm going to have mvx dot minus c. Then I'm going to have the x component of this guy here, where the x component of that is this times vx. So I'm going to have here vx squared vy squared square root vx. Okay. Then in the y direction, I'm going to have m vy dot minus mg minus, because the gravity only acts in the minus y direction, and c. Then again, what I do is I look at the y component of this. That's this times that. And so what I'm going to have there is vy. Okay, so those are my equations. I can divide by m in order to get equations that are just in terms of vx dot and vy dot. Okay. So if I do that, I get these equations here. Vy dot is equal to c over m times this thing here times vx. Vy dot is equal to minus g minus c over m, the speed times vy. Okay. So in general, these equations are first order differential equations. They're ordinary differential equations because they have an ordinary derivative. Because of the square root, they're nonlinear differential equations. And also they're coupled, meaning that vx dot depends on both vx and vy dot depends on vx and vy. So that makes the very general projectile motion, difficult problem to solve. You cannot solve it on a piece of paper. You need to use a computer to solve that, which we'll do in a minute. What I'm going to do here is but before I first so I'm going to look at two solutions. One, I'm going to look at a simplified case of just taking an object and dropping it, okay? In that case, we can get an analytic solution. But before I do that solution, let's consider this idea of a terminal speed. If I take an object and drop it, there are going to be two forces acting on it. So if I take this object and I just let it go, there's going to be the quadratic air resistance and then the weight acting down on it like that. And what's going to happen is at some point the object is going to stop accelerating. And so that means that Vy dot is equal to 0. If I take that and substitute it into equation 2, what I get from that is that G is going to be equal to C over M. Now, again, since I'm just dropping it, Vx is equal to 0. So I'm going to get Vy squared square root times Vy. And that's going to give me V squared. And I'm going to say that occurs at a special speed called the terminal speed. That allows me to solve for the terminal speed. It's just mg c and square root. Okay, so that's the terminal speed. So I would expect that if I want to solve, for example, equation 2 for just dropping an object with quadratic air resistance, I want to solve for Vy as a function of time. I would expect that in the limit as t goes to infinity, my solution, whatever that solution should be, Vy should go to V term. Okay, where V term is given by this quantity right here. Okay, so that's good. At least I know what the limiting solution should be. Okay, so what I'm going to do is I'm going to solve this equation just for dropping the object. Okay, and let's rewrite that equation. I'm going to rewrite 2. So I'm going to get here Vy dot, Vy dot. So Vy dot is equal to, so we have, now we got to be really careful here. Okay, for this particular, we have to look at this equation. Now this is the very generic equation, but if I'm going to look at it just for one-dimensional motion dropping, if I just drop an object, be really careful about signs. Okay, this minus sign here is for a coordinate system where what I drawn earlier, but in the end, the component of this is going to, remember, this thing should always oppose. Now, if I'm just going to drop an object, I got to be really careful because now in the direction of motion, G doesn't, this is no longer negative, it's actually positive. So I have to be careful. So I have to write here, what I'm going to get here is I'm going to get G, all right, because when I drop the object, now I'm actually flipping my coordinate system, so it goes down. And then I'm going to get here, again, I have to have the minus there because it opposes. If these were the same sign, then that would have a problem. C over M. Vx is equal to 0. And then I'm going to get Vy squared. Okay, so that's the differential equation I want to solve. Now, I can identify a couple things. I'm going to factor out a G here. I'm going to get 1. And then actually, what I'm going to do is this. I'm going to write here G over G. If I factor out a G, I'm going to get C M G Vy squared. Okay. Now, notice that this guy here, mg divided by c, that's 1 over v term squared from this equation here. So I can write this guy here as g 1 minus v squared divided by v term squared. That's cool. Now we got everything in terms of nice physical units, v terminal velocity. Okay, so this is my equation I have here. And so what I want to do is I want to solve that equation. Okay, so it's a first order. It's a first order nonlinear differential equation, but I can actually solve this by direct integration. So let's just write it like Vy dt is going to be equal to G. Again, V term is a constant. I'm going to use separation of variables. So I'm going to get here. What I'm going to do is I'm going to divide by that term, and I'm going to get all the v's on one side and all the t's on the other side. So I'm going to get G dt minus 1 over the quantity v term. It's Vy squared. Okay. Vy. Okay. And I'm going to integrate that from 0 to time t. And I'm going to integrate this from 0. Again, I assume the initial condition is 0. So what am I doing? I'm dropping it. So that means that Vy at times t equals 0 is equal to 0. And also I assume that, well, this will come later. I started my, okay. So if I do that, then what I'm going to get is I'm going to get gt, and then this guy here, you can look that up. That is a arctangent. Okay, so I'm going to get I'm going to get v term times, by doing that integral, I'm going to get v term. You can look that up, or times the arctangent of v over v term. Okay, and then you can solve for v. This is Vy. Vy, again, this is Vy using the notation we have. Vy of t is the, Vy of t is equal to v term times the hyperbolic. So actually, sorry, this is not, I made a little mistake. Sorry, it's not an arctangent. It's a hyperbolic arc hyperbolic tangent. Okay. So, okay. And you can get that. You should learn that in calc class, but okay. And then I get here gt divided by v term. Okay. So I solved this just by direct integration. Now, again, remember, how do we check our solution? That's important. Remember that Vy, as t goes to infinity, Vy should go to a v term. Okay. So looking at this equation, this is this times this. That must mean that the hyperbolic tangent, what I would expect is the hyperbolic tangent to go to 1 as t goes to infinity. Okay. Now you may not know your hyperbolic tangent functions and forget this stuff too, but what we can do is we can plot this stuff, and we could use a computer to plot this. So what I'm showing you here is I'm plotting hyperbolic tangent. Okay, so this is a hyperbolic tangent as 0 as a function of x, as x goes from 0 to 50, and notice that the function increases linearly and hits 1. So as I go further and further, so that shows that this function does satisfy that. So that's good. That's cool. You don't need to see all that. Okay, so that means that this function does do that. So then as t goes to infinity, this goes to 1, and then we reach our solution. Cool. Now, let's go back and let's take a look at these guys here. Okay, so I'm going to copy that. Okay. And then I'm just going to paste it here. Okay, so let's look at the generic solution for projectile motion. All right. Now, again, I get this for first order differential equations. They're nonlinear and coupled. I cannot solve that using a computer. Sorry, I can only solve it using a computer. So what I want to do is look at the computer solution, and we'll do this in recitation. But what the hey, let's just do it here. Let me bring up Spider again. Okay, so what I have here, okay, so what I'm going to do is this is my Runga cutter for solving. And again, what I'm going to use, like we did previously, is using the ODE class in SciPy Integrate to solve. Okay, and so my code, what I do is I first import all the stuff I need. NumPy for all the numerical stuff, SciPy Integrate ODE for solving, Matplotlib for plotting, and I'm going to use some other stuff for displays, and then this is for making movies, which we talked about before. I'm not going to worry about that. Remember, this is the special little library that I wrote for this class. Okay, so this solves for projectile motion for quadratic air resistance for baseball. Okay, so I'm going to take a baseball, I'm going to shoot it with a certain speed and at a certain angle with respect to horizontal. So G is the acceleration to gravity, D is the diameter of the baseball, gamma is the coefficient of quadratic air resistance for air, M is the mass, C is again the constant, gamma times D squared, and then this is the terminal velocity. And the reason why I write that there is this as to compare my numerical solution. Okay, going back to what I had before, remember these are my two coupled differential equations. Okay, I've written as first order coupled differential equations, so that's cool, because then what I can do is solve these, and so then I create a function called DE, where y0 is Vx, y1 is Vy. DE is y represents the coupled differential equation, so the first element d y0, so basically the way we write it is the Vx dot equals this, and that should be the first element, the y, which is the same thing I have right here. Okay, and then here the second element is the derivative of Vy, that should be this thing here, and that's what I have here. Okay, again, now I have to set up initial conditions. I'm going to solve this differential equation for 2,000 points. I'm going to do it over a total range of 20 seconds. I'm going to create an interval of 20 seconds divided by 2,000 so my time increment, and I create an array of times. Okay. Now, before I solve it for just generic projectile motion, I'm going to do it for just dropping. And I'm going to, well, I pick some initial height, but it's zero initial speed. And what I'm going to do is, yeah, I'm just going to solve that equation there. Okay. So then I have to create my arrays for my solutions. Vy, okay, what is y0? Y0 is the x component of the speed of the velocity. Y1 is the y component. And then I append this. This is the initial condition for Vx0. Well, that's going to be 0 because, oh wait, what did I do there? Oh, this is just a generic projectile motion. Okay, so what I'm going to do here is I have some initial x position. This could be 0, it could be anything. I'm going to start some initial height. It could be 0, I picked 1,000. I give it an initial speed of 0, so that means that the object is stationary. Theta doesn't, I have a theta here, that doesn't make any sense, but since I'm just dropping it, I get 0 times that theta. So this is, again, just free fall, or just dropping an object. Okay? So what I'm going to do is I'm going to set my arrays. These are my arrays of solutions. This is the x component of this velocity. This is the y component of velocity. And then I append my initial conditions. Again, my this array should be always zeros because it's not moving in x. And then really what I'm interested in is y1. Okay. I'm going to use Dopin Dopre or domain prints 4-5 to solve. You can use any ODE solver. Again, this sets up R. R is my thing of my class ODE, and then DE is my functional form of my ordinary differential equation. This sets the back end, which is domain prints. You can use any back end. This sets the initial values. So the initial values are the initial component of the speed, the x component, y component, and time t equals 0. Then what I do is for every time in my element t, so tt is just a variable, an element of t, and I start at 1 because I see if I start at 0, that would start at the initial time 0. I know the solution at the initial time, so I'm going to start at 1. And then this is the main line right here. This solves it. And then I take the solution. So this is an array of 2 elements. Solution 0 is the x component. Solution 1 is the y component, and I append. Then what I do is I take the solutions and create them as numpy arrays vx and vy. Then, okay, well, I'll talk about this, but then I calculate x and y just by direct integration. Remember, once we have, just going back to here, once we have these guys here, I can, well, what am I saying? If I have, if I have Vx as a function of time, okay, but then if I want to get this, how do I do that? Well, Vx is equal to dx dt, and so I can calculate x of t as a function of time is the integral from 0 to some time t, Vx of t, t prime, dt prime, plus my initial condition for the constant. And I can do that same thing for y as a function of time, except for y, what I have is so I can just integrate directly the solutions. Now, since in a computer I don't get an analytic form, I have to do the integration. I'm going to use cumulative sum to do that. Okay, then I calculate the no error resistance solution just as a comparison, and let's plot. Okay, so I'm going to run this code. Okay, and so this first graph shows me the height is a function of time. Remember what I do is I start at a height of 1,000, and after 20 seconds it drops from 1,000 to 400. So that's y is a function of time. Let's look at the speed, or well, since it's only moving one dimension. Notice that at times t equals 0, so this is vy, or since vx is equal to 0, it is equal to the speed. Notice that I drop it, so it's equal to times t equals 0. And then notice as it kind of comes, it does this type of thing here, asymptotically hits. And the red line is v term, and v term, I calculate it just the way we showed before. That's equal to 34.6, and that's what I have there. That's pretty cool. So what I can see here is that this thing, it does reach an asymptotic solution, and it does hit the number I expect. And that's a good way of checking your numerical solution. All right. Now, just to end, let's take a look at the solution for not dropping it, but for some actual projectile motion. So I'm going to comment this, and I'm going to uncomment all this stuff here. And so what am I doing? I start at the origin, 0, 0. I have initial speed at 30 meters per second. I'm going to launch it at 50 degrees with respect to the horizontal. These are my initial components. So I'm just going to solve that again. All right, and let's take a look what we have here. So here we see the height is a function of time. Obviously, it goes up and hits the ground pretty quickly, much quicker than before. Let's actually rewrite this. So let's see, 5 seconds. Let's plot that guy there. That is figure 1. And what I'm going to do there, height versus time, I'm going to say PLT xlim from 0 to, say, 5. Okay, let's just run it again and see if that works a little better. Yeah, I noticed that we got that bad business going there. So we can say PLT Y lim from 0 to say 50. Obviously it doesn't go negative. All right, good enough. All right, there's my projectile motion. Okay. Oh, I did it here too. Okay. Again, I plot the y component of the speed. Now there's an x component and a y component. Okay. Hey, why not? For giggles, let's do this. Let's do. So this is the type of stuff you guys should do with this code is think, hey, what does this look like? Hey, what does that look like? I'm going to call that 3. So I'm going to plot the x component. And then let's call this 4. Let's see if I can do this on the fly. And then this is x is a function of time. Or Vx. So let's just run and see what happens. Okay, well, so we still see, what am I plotting there? Vx. Oh, we didn't do it over. Huh, that's interesting. Okay, well, I'm not sorry about that. The thing I really want to show you is the comparison of the trajectory for with and without air resistance. You can see here that this guy, you can see that the range actually decreases quite a bit with air resistance compared to without air resistance. Okay, so now what I want to do is actually show you. Now, again, what we just got done looking at was kind of showed you a static picture of comparison of projectile motion with and without quadratic air resistance. What I want to do is I want to look actually at a dynamic movie. So what I did was using that movie plotting routine in that Physics 552 library, I'm going to plot projectile motion with and without air resistance. So I have here, this is the height, this is the range, and let's take a look. So you can see here that initially two objects are on top of each other. You can see that the blue object is without air resistance, the red object is with air resistance. You can see that air resistance causes the horizontal component of the velocity to slow down. And that, of course, for without air resistance, there is no force in the horizontal direction. And you can see here that, again, the range is smaller, time of flight is smaller. Okay. So that's a good comparison, just a good comparison between the two. You can do that using the code. If you take a look at the code here, built into this, so remember I said I had this little library here called 522, which you guys should have as a module. We talk about modules in Python. You should be able to use this, and we'll be using this throughout the semester. In this bad boy here, I have a little code, and that code is called physics animate trajectory. I wrote that. It animates a trajectory. Phys is what is phys? Phys is I give this thing an alias. I basically say import phys 522 as phys. That's my library. And then 522 is here, and there's a bunch of fun stuff in here which we're going to use throughout the semester. I don't want to go with, you don't need to know how this stuff works. Just use it. All right. And so what I have here is I'm going to plot it. And then I make a statement here is every time I run it, I don't want to plot it. And so what it will do is sometimes when I want to plot it, it'll do it. It will plot it, and then it will save it to a file. Okay? And the file location I save it to is that guy right there. Okay. So what we did was, again, just kind of summarize what we did. We looked at the equations of motion for quadratic air resistance. We got fairly complicated coupled nonlinear differential equations. We could write an analytic solution only for dropping an object or one-dimensional motion. Okay, and that's what we did here. And we showed that the one-dimensional motion solution was a hyperbolic tangent. Okay, and that behavior of that hyperbolic tangent asymptotically went to terminal velocity. So it did, the solution did go to what I expected to. Okay. If we look at the more complicated solution where I have projectile motion, I cannot solve this analytically. I have to use a computer to solve it, and then I will get from that Vx and Vy. But once I have Vx and Vy, I again can use a direct integration to get x and y as a function of time. And we did that using Python. This program called projectile motion quadratic drag, which you can find on Canvas, and we'll talk about that in recitation. And I plotted the solution for projectile motion compared it to that with air resistance, and we made a nice little movie of that. Okay, so this is Brian Washburn signing off. Take care. Bye-bye.